This video is going to go over Kepler's laws and orbits. Now, Johannes Kepler made these laws of planetary motion. They tell us about the orbits of planets around the sun. They can also tell us about the way stars orbit around galaxies and all kinds of things like asteroids and comets. They make us understand how things move out in space, how we can predict them. So first, before I start talking about the laws, a question some people have is, why does the Earth orbit the sun? How come it doesn't just fall right into it? Like we are on the Earth, and when we jump, we don't orbit the Earth, we just fall right into it. So let's oversimplify this. Let's say the Earth is already formed and it's flying through space at some speed or some velocity, some direction, which would be a speed. According to Newton's first law of motion, it's going to move in that direction at that speed forever, unless an external force is applied to it. Now let's say that that planet Earth happens to go by the sun. Well, the sun has a force of gravity pulling the Earth towards the center of the sun. And so the Earth has two different forces working. The force of it moving this way, according to this picture, sideways, and getting pulled towards the center. So what will end up happening is both forces will kind of mix, and you will get an orbit around the sun. Now, in the old days, people thought that the orbits were perfect circles. But that brings us to Kepler's first law. The first law is the law of ellipses. Each planet's orbit around the sun is what's called an ellipse. Make sure you write this word down for your vocab. That means that it's more like an oval shape. And now the ellipse, the way it works is at one focal point, it's always on the sun, another focal point is closer to the other end of the orbit. We call these foci, it's the plural of focus, focal point. And the center of the orbit somewhere here. I'll take that away for now. And what we learn here is that the orbits can be more or less oval shaped based on where these focal points are. One will always be on the sun. But if you have a focal point that is very far away, right? Let's say it is all the way over here, and the other one's always going to be here, then we are going to get a much bigger oval shaped orbit. We call this eccentricity. Now, the eccentricity, as you saw from your content page, can be between 0 and 1. So closer to 0, you think of it like this, 0 is a circle, means it's going to be more circular. More circular. And when you have that, what you'll find is that the focal points end up being pretty much right next to each other. That would make a very circular orbit. Now, the closer to 1 the eccentricity is, the more ovular it is. So that would mean that the focal points are further away. So higher eccentricity means more oval shaped. Lower eccentricity, closer to 0, means a more circle shape. Now from this, we get a couple terms. This area here, we call that the semi-minor axis. Just a very simple term to describe when the shortest distance there. And here we get the semi-major axis. Just the distance where it's furthest away. There's also other words. Perihelion. Perihelion. My computer's lagging a bit, messing up my writing. Perihelion is when the Earth is closer to the sun, and aphelion is when it is further away. Sorry for the lag. Those are just terms, very easy to learn. But if you don't know these terms, you get confused when people talk about these things. But they're very easy terms to learn, so make sure you make it a point to learn them. Okay? So that brings us to the second law, the law of equal areas. No matter where the planet is around the sun, if you were to count, let's say 1 second, right? Over every second, that planet is going to cover the same area. If you drew a line from the planet to the star, it's going to cover the same area over the same amount of time. So like 1,000, 1,000, 1,000, 1,000, 1,000. So that tells us that if you know where the planet is in its orbit, then you can calculate the speed. Because the further away it is, aphelion, near the semi-major axis, it's going to be traveling slower and make a thinner, however much longer triangle because it's further away. But the closer that the planet is to the star or our sun, then the faster it's going to move. So it's not going to make as tall of a triangle, but it's going to make a very wide triangle. So although the speeds are different, the area of space that the planet covers is always the same. All right, so it tells us that the planet in its orbit goes different speeds. Not only is it at different locations, it's going different speeds. Now, the last law is the law of harmonies. The square of the orbital period is proportional to the cube of the semi-major axis. So what that means, there's a little equation we have. A cubed, which is the semi-major axis, right? The distance, the semi-major axis cubed, equals the period squared. Now, period is just how long it takes to complete one orbit. A, which is the semi-major axis, will be in astronomical units, AU, and P is going to be in years, Earth years, okay? So if we know that the amount of time it takes, let's say we know the semi-major axis. We know how far the planet is of the semi-major axis. If you know that A equals 3, then you can figure out how long it's going to take for that planet to orbit around that star. So if A equals 3, then 3 cubed will equal P squared. 3 cubed, 3 times 3 times 3 is 27, equals P squared. Now I'm not sure what the square root of 27 is, but we can figure it out. 5.196. All right, cool. So then we will know that to get P, we just take the square root of both sides, and P, the period, the amount of time it takes for that orbit to happen, is 5.196 Earth years. It's crazy because for any planet, this equation holds true. If you have any questions, ask me. We are going to go deeper into this with the gizmo, but I just want to give you a quick overview.